You walk past a municipal hall built before 1920, heavy brick, stone cornice, a roofline meant to look finished. You look up and see the oddity, a stubby rooftop tower with pipework and a cast-iron crown, and ceramic insulators spaced like a measuring template. People offer the casual explanation, just a vent stack. Maybe a lightning rod, maybe decoration. But vents do not usually need insulated standoffs, symmetrical spacing, and multiple parallel runs of pipe that never actually exit like exhaust should. And lightning rods do not typically route into the building through valved manifolds and clean, repeatable mounting plates. So what are you really seeing, ornament or a system interface? The promise is this is not vibes. You can trace it through surviving rooftop hardware, interior routing scars, and the paper trail of codes, catalogs, and municipal maintenance language. Start with a downtown bank block from the 1890s, a Chicago-style commercial street. The kind of building everyone photographs for historic charm without noticing the technical layer. Look at the roofline. There is a decorative tower, they will tell you, but zoom closer. That tower has flanged pipe collars with bolt circles still visible under decades of paint. Around each collar, you see paint failure halos, the kind that form when metal expands and contracts under operational stress, not static display. The symmetry is too tight, 6 mounting points, evenly spaced, each with identical hardware. Compare this to an actual vent stack on the building next door. Real vents show soot staining, random placement for draft optimization, and simple penetration caps. They slope for drainage. This tower shows none of that. Instead, geometric precision, insulated standoffs, and what looks like distribution logic. Period architectural specification sheets from the 1890s describe vent stacks in detail, material requirements, placement rules, and cap designs. This does not match. But compressed air system manuals from the same era show nearly identical mounting geometry for rooftop receiving apparatus. The language is careful, the function modest, but the hardware is recognizable. If it is venting, where is the exhaust signature? The weathering patterns suggest intake, not exhaust. The mounting logic suggests controlled distribution, not passive release. The first contradiction is simple. Materials and placement do not match the label. Walk 3 blocks to a pre-1920 apartment block, New York style, courtyard tenement. Same era, different building type. Look at the cornice line. There is decorative metalwork running along the brick, except that the decoration includes ceramic insulators on metal standoffs, keeping conductors away from masonry. Small white porcelain pieces, weathered but intact, spaced at regular intervals. You have been told it is just decorative metalwork. But insulation is a functional choice. Ceramic isolates. It prevents current flow or leakage. Decoration does not need isolation, it needs visibility. Electrical and telegraph supply catalogs from 1900 to 1915 list these exact insulator forms. They are standard components sold by the gross, with specifications for voltage isolation and environmental durability. Building trades journals describe them as necessary apparatus for atmospheric collection points in some entries and auxiliary conductor mounts in others. The language shifts depending on the publication, but the hardware remains consistent. Count the spacing. Every 8 feet, there is another mount. Across 3 facades, the pattern holds. That is not ornamentation following aesthetic whims, that is engineering following distribution logic. If this were merely decorative, why would a building owner pay for non-conductive standoffs? Why insulate metal that is only meant to be seen? The mounting method implies controlled routing. Insulation is a functional signal, not a style choice. And once you notice it here, you start seeing it everywhere. Same insulators, same spacing, same careful separation from building structure. Shift to the early 1900s to a factory loft in a New England mill town in the textile district. These buildings were built for function, not flourish. Efficiency mattered. So when you see rooftop piping with valves, T's and unions, serviceable hardware with access clearances, the old plumbing leftovers explanation starts to crack. Plumbing shows drain routes, it follows gravity, it terminates at fixtures you can map. This piping runs horizontally, branches symmetrically, and penetrates the roof at multiple points with identical fittings. The valve bodies are brass, built for pressure regulation. The unions allow disassembly for maintenance. The whole assembly is designed to be serviced, not abandoned. Compressed air system handbooks from 1905 to 1915 describe exactly this arrangement. Rooftop header lines with distribution drops, valved for zone control, unioned for seasonal maintenance. Plant engineering manuals show diagrams that match the surviving geometry. Not perfectly, but close enough to suggest a common design language. Follow the pipe direction, it runs toward roof penetrations, then disappears into the building envelope. Inside the top floor, if you know where to look, you will find patched wall scars and bracket ghosts where risers once descended. The number of drops matches the valve count on the roof. If this were abandoned plumbing, why maintain serviceability? Abandoned systems get capped, cut, or ignored. This was designed for ongoing access. Manifolds exist to manage flow, not decorate roofs, and the placement, always near stair cores and near vertical chases, suggests someone planned for distribution, not display. Inside a courthouse from the 1910s in the American Midwest, the top floor shows renovation scars. Patched walls where conduit once ran, bracket ghosts in regular intervals, pipe chases that dead end at the ceiling, cut flush and plastered over. You have been told these are renovation artifacts, generic traces of building updates. But renovation leaves random scars. This is systematic. The routing aligns with the rooftop interface. Measure the spacing, every 12 feet, another mounting point. The chases follow load-bearing walls, not partition lines. Someone wanted permanent paths, not temporary fixes. The pipe diameters are consistent, 1 inch and 2 inch. Standard sizes that match period catalogues. This is standard. Renovation permits from the 1950s and the 1960s, when these buildings were modernized, list removal of obsolete apparatus and mechanical system updates. Insurance inspection notes from earlier decades mention atmospheric auxiliary equipment and supplemental distribution. The language is careful, the details sparse, but the implication is clear. Something was installed, then removed. The implication remains. If nothing powered anything, why does the building show a distribution plan? Why route systematically when aesthetics would allow random placement? The building keeps a memory. Plaster can cover mounting points, but it cannot erase the logic of placement. Routing scars do not lie, they trace intent, showing where hardware once connected rooftop interface to interior distribution points. Remember the memory, look for bracket pairs, one high and one low, suggesting pipe runs that descended in stages. Look for regular spacing of penetrations. Look for fastener types that match across multiple locations. The pattern is there, faint but readable, telling the story of a system that was. Now step back and look at the skyline of a rail-adjacent city corridor. St. Louis, Kansas City, similar Midwestern hubs from 1890 to 1915. Hotels along the transit lines, office blocks near the station, municipal buildings in the civic core. And across all these different building types, the same rooftop silhouette, a tower with identical finial base plates, the same ceramic isolators, the same flanged collar geometry. The parts are identical. If this were architectural fashion, you would expect variation. Architects compete through style differentiation. But fashion does not standardize hardware down to bolt circle diameter. Fashion does not repeat insulator type across cities and building programs. Standardization suggests something else. Manufactured components ordered from catalogs, specified by function rather than aesthetic preference. That is standardization. Hotel engineering journals from 1900 to 1910 List atmospheric apparatus and auxiliary receivers in procurement columns. Trade catalogues show mounting hardware with spec sheets, base plate dimensions, insulator ratings, pipe thread standards. The language describes standard installations and typical configurations. Replacement parts could be ordered by catalogue number. Check the catalogues. Why do banks, hotels, and municipal buildings share the same ornament? Because ornament does not need replacement parts. Systems do. Fashion varies by architect, by region, by decade, but this hardware holds consistent across all three variables. Photograph 3 sites, compare bolt circle diameters, check insulator forms, measure pipe sizes, they match. Repetition across building types implies standardized system components, not decorative trends. The question shifts from what does this represent to what system required this standardization. Look at placement logic across a city's 1900s municipal buildings. If these rooftop towers were centerpiece ornaments, you would expect them positioned for maximum visibility, centered on the primary facade, aligned with street views, highlighted by cornices or parapets. But they are not. They sit near stair cores, they align with service shafts, they occupy positions that prioritize vertical routing over aesthetic impact. Functional placement prefers logistics. Ornamental placement prefers visibility. These towers consistently choose logistics. Building code sections from 1905 to 1915 specify that mechanical apparatus must be located near existing shafts to minimize structural penetration and simplify distribution. Lightning protection, by contrast, requires elevation and isolation. It needs the highest point, away from service areas. Check a building's roof plan against its interior stairwell location. The tower sits directly above or adjacent to the main stair shaft, the only continuous vertical path from roof to basement. That is not coincidence. That is routing efficiency. The placement allows pipes or conduits to descend through existing chases without cutting through occupied floor plates. Period construction drawings, when available, show these towers marked as apparatus mounts or service interfaces, not ornamental features. The distinction matters. Ornament gets detailed in elevation views. Apparatus gets detailed in mechanical sections with pipe routing and equipment schedules. If it were just a finial, why sit it where it is easiest to pipe downward? Why consistently choose function over form? The answer is that placement follows logistics, not ornament rules. Once you recognize the pattern, it becomes impossible to see these towers as mere decoration. They are positioned like system components because, in fact, they were. In the basement of a downtown department store from the 1910s, there is a room that does not quite make sense anymore. Concrete plinths anchored to the floor, bolt patterns drilled in regular geometry, oil stains in circular patterns, the kind left by equipment bases over decades of operation, vent grills in the walls, sized for equipment cooling, but the equipment is gone. The casual explanation was that it was an old safe base or maybe old boiler gear. But safes do not need oil. Boilers do not bolt down in multi-point patterns suited for vibration control. And the bolt layout matches regulator stands and reservoir-based diagrams in equipment catalogues from 1905 to 1920. The spacing, the diameter, the number of anchor points are all consistent with pressure regulation and storage apparatus, not security or heating. Municipal approvals from the era sometimes list pressure system installations with insurance requirements for safety equipment, relief valves, and monitoring provisions. The room layout supports this, with equipment space, service clearance, and ventilation for mechanical operation. This was a control station. Trace upward. Above the basement room, a vertical chase runs toward the roof. The chase is now filled, but building records show it once carried risers. On the roof, directly above, the familiar tower with its insulated mounts aligns with the interior evidence. The connection is readable. Rooftop interface, vertical line, interior cabinet for regulation and storage. Absence becomes positive trace. You do not need the machine to identify the machine room. Footprints, mounting logic, and spatial requirements all remain. The room remembers what it held even when the equipment has been salvaged. And that memory, combined with rooftop evidence and documentation fragments, triangulates toward a system that was real, functional, and eventually removed. Late 1800s transit buildings, stations, post offices, and rail-adjacent hotels show the same pattern, but denser. Rooftop hardware, street-level grills, subfloor chases, and service corridors with regular penetrations. This is not isolated apparatus anymore. It starts to look like network infrastructure. Networks require nodes and distribution points. They require standardization for interoperability, maintenance access, and systematic placement. And they cluster along routes where logistics and coordination are strong, exactly where these installations appear. Railway engineering journals from 1890 to 1910 describe atmospheric systems as auxiliary infrastructure useful for signals, controls, and small actuators where electric power was unreliable or unavailable. Municipal infrastructure reports list distributed apparatus in civic buildings installed during the same narrow time window. The language is modest, the claims limited, but the geographic pattern is clear. Transit corridors, civic centers, and commercial districts. Map the occurrences. They follow rail lines. They cluster near telegraph offices. They appear in buildings with coordinated management, institutions, chains, and municipal networks. And they all date to before 1920, before electrical standardization made alternative systems redundant. What system benefits from being supplemental, distributed, and serviceable? One that filled gaps in emerging infrastructure. One that worked alongside, not instead of, primary power. One modest enough to be maintained locally but standardized enough to be replicated across sites. Think of supplemental systems that supported primary networks. The pattern stops behaving like architecture and starts behaving like infrastructure. Not grand, not revolutionary, just practical, widespread, and eventually obsolete. The buildings still carry the markers, but the system itself has become invisible, reclassified as ornament because the function is no longer recognized. In the archives of an 1890s City Hall annex, procurement ledgers tell a different story than the buildings do today. The rooftop tower, now called decorative ironwork in historic surveys, appears in period records under mechanical apparatus. Line items list receiver installation, regulator cabinet, and distribution fittings. These are not aesthetic purchases, they are system components. Maintenance notes from the 1900s to the 1920s describe servicing. Apparatus inspected, valves replaced, insulator cleaning. Decoration does not get maintained on schedule. Systems do. Council approvals reference atmospheric auxiliary equipment with safety compliance language. Insurance inspections note pressure apparatus with required relief provisions. Maintenance records make the difference. The terminology itself is forensic evidence. Compare decorative line items in the same ledgers, cornice detailing, ornamental ironwork, and facade embellishment. Different budget categories, different procurement language, different maintenance schedules. The rooftop hardware was not filed with the decoration, it was filed with the mechanical systems. Why did the language shift? Because when a system becomes obsolete, its technical terms lose meaning. Atmospheric apparatus becomes old metalwork. Distribution interface becomes decorative tower. The function is forgotten, so the vocabulary simplifies into whatever makes casual sense. The physical object remains, but its name changes to match current interpretation. Obsolescence reshapes language. Search archives for keywords like compressed air, pneumatic, receiver, regulator, and atmospheric collection. When you do, you find scattered references, not abundant but present, enough to confirm that the terminology existed, that the systems were documented, and that the installations were real. The paper trail is thin because the technology was modest and supplemental, not revolutionary. But thin trails are still trails. They lead directly to the hardware still visible on the rooftops, now stripped of its original name, but not its original form. Patents from 1895 to 1915 show exploded diagrams of rooftop collection apparatus, insulated mounts for atmospheric intake, valved headers for distribution, interior cabinets for regulation and storage. The drawings match surviving installation geometry closely enough to suggest common design principles, even if specific manufacturers varied. One patent describes apparatus for collecting and distributing atmospheric pressure for auxiliary mechanical purposes, suitable for building installation where supplemental power is advantageous. The language is careful to emphasize low-power applications, pneumatic signals, control actuators, small tools, and document tube systems. No miracle claims, no revolutionary energy promises, just modest, practical supplementation. Compare patent drawings to surviving bolt patterns. The insulator layouts align, the valve placements match, the cabinet footprints correspond. This is not proof of universal adoption, but it proves the concept was developed, documented, and physically realized in manufactured hardware. The parts existed, the installations happened. What were they powering? Period sources mention building signals, pneumatic message tubes, control systems for ventilation dampers, actuators for mechanical clocks, and small workshop tools, all modest applications, all supplemental to primary building systems. The scale matches the evidence. Limited distribution, local regulation, maintenance intensive but manageable. Why choose AIR over emerging electrical systems? Early electrical infrastructure was unreliable, dangerous, and unevenly distributed. Compressed air was familiar from industrial contexts, relatively safe at low pressures, and could be locally generated and stored. It was not better forever, but it filled a gap during a narrow window when buildings needed supplemental power and electrical systems were not yet standardized. The patents do not prove every rooftop tower was functional, but they prove the technology was real, the hardware was manufacturable, and the installation logic was documented. When you see the same mounting patterns in surviving buildings, you are seeing the physical implementation of these documented designs. The concept existed, the parts remain. A hospital building from the 1910s shows something crucial: pressure-rated fittings, relief valve seats, drain points at low elevations, and threaded connections that match contemporary boiler and compressed air standards. Decorative metal does not require relief logic. Pressure systems do. Building codes from 1905 to 1920 specify safety requirements for pressure apparatus, including relief valves, pressure gauges, drain provisions, and inspection access. Insurance rulebooks list equipment standards and installation requirements. The surviving hardware, when examined closely, shows compliance with these standards. Thread types match period specifications, valve bodies show pressure ratings, mounting methods follow safety code logic. But here is the limit: these systems were maintenance heavy. Air leaks, fittings corrode, pressure regulation requires constant attention, power density is low compared to electrical systems, which meant more infrastructure for less output. Noise was significant. As electrical grids standardized and became reliable, the advantages of atmospheric systems evaporated. The paper trail explains why it stayed supplemental. This was never going to replace steam heat or electric lighting. It was useful for specific applications during a specific window, then became obsolete not because it did not work, but because something better arrived. The technology was real. The limitations were also real. If it was so practical, why did it lose? Because practical does not mean optimal. By the 1920s, electrical systems offered higher power density, lower maintenance, quieter operation, and better scalability. Atmospheric systems could not compete on those terms. They worked, but they did not win. Codes and safety standards proved these were legitimate systems, not fantasies. The same documentation shows the constraints that limited their growth. The evidence cuts both ways. Yes, the systems existed. No, they were not miracle solutions. They were modest, functional, and ultimately unable to compete with the next generation of building infrastructure. That is not a conspiracy. That is how technology succession works. Manufacturer catalogs from 1900 to 1915 list standardization in parts, including insulators in 3 sizes, flange assemblies with common bolt patterns, valve bodies with interchangeable trim, and mounting brackets in pre-drilled configurations. Standardization meant parts could be ordered, replaced, and specified without custom fabrication. Supply houses listed these items by catalog number. Contractors could source them regionally. This is how you know it was a system, not a series of one-off experiments. Systems require standard parts for maintenance and expansion. Decorative elements vary. Functional components standardize. And the hardware visible today, the insulators, flanges, and mounting brackets, shows consistency that only makes sense if they were manufactured products, not architectural ornament. Cross-compare surviving hardware dimensions to catalog standard sizes. The bolt circle diameters match. The insulator forms appear in supply listings. The thread standards correspond to period industrial specifications. The parts are recognizable because they came from recognizable sources. Manufacturers who produced apparatus for building systems, not sculptors who created unique architectural details. If standardized parts existed, what force standardized them out? The same force that replaced gaslights and iceboxes, superior alternatives. By the 1920s, electrical infrastructure had improved dramatically. Reliability increased, safety improved, power density made electric systems more versatile, and critically, electrical utilities offered centralized generation and distribution, eliminating the need for building-level apparatus. Atmospheric systems required local generation, storage, and maintenance. Electric systems required connection to a grid. The grid won, not because atmospheric systems were fake, but because centralized electrical infrastructure was more efficient, more scalable, and less maintenance-intensive. Standard parts leave standard scars. The geometry repeats because the hardware repeated. The mounting patterns persist because the installations followed manufacturer specifications. And the fact that you can still match surviving hardware to period catalog dimensions proves the system was documented and widely implemented before it was decommissioned, salvaged, and relabeled as something it never was, mere decoration. By the mid-20th century, renovations sweep through these buildings. Rooftop shells remain. They are architecturally distinctive, structurally integral, and difficult to remove, but interiors show cut risers, patched penetrations, and asymmetric salvage. Valuable components like brass fittings, copper pipe, and regulator assemblies are stripped. What remains is reclassified. Renovation specifications from the 1950s to the 1970s list removal of obsolete apparatus without specifying what it was. Scrap records show salvaged metals but no system names. Trade modernization articles describe updating mechanical systems in language that assumes everyone knows what is being replaced, so no one bothers to document it precisely. The knowledge becomes implicit, then lost. The sequence is straightforward. Installations stop when better alternatives emerge. Decommissioning follows. Valuable components get salvaged. Remaining shells, stripped of function, are relabeled ornament because no one remembers what they did. Manuals stop teaching the technology. Expertise retires. Within a generation, the system becomes invisible. This is not conspiracy. This is succession. Technology changes and buildings adapt. The physical layer lags behind the functional layer, leaving traces that outlive their original meaning. You can still read the old system in mounting geometry, routing logic, and systematic absence. The buildings are palimpsests, new uses written over old infrastructure, but the old infrastructure is still visible if you know how to look. Compare buildings modernized early versus late. Early renovations often removed everything, leaving only rooftop shells. Late renovations sometimes left interior routing intact, but abandoned in place. The degree of removal varies, but the pattern holds. The functional core is extracted, the architectural shell is retained, the rooftop tower is still there. Walk past it again. Same silhouette, same ceramic insulators, same flanged collars, but now it reads differently. Not as decoration, but as interface. Not as mystery, but as trace. Obsolete does not mean imaginary. It means a better alternative one.